All right, chemistry. This is your video lecture for Chapter 2, Section 3. This is titled Using Scientific Measurements. Your first objective is to be able to distinguish between accuracy and precision in terms of measurements. In science, those are considered two different things, and we'll describe that in depth later. Determine the number of significant figures in a measurement and apply the rules for significant figures in calculations. That'll be a topic that will stay with us for the rest of the year, so hopefully this sinks in early. Calculate changes in energy using the equation for specific heat and round the results to the correct number of significant figures. As I've said before, we will be using the equation for specific heat, but do not fret. This is not going to be a full-on thermodynamic unit. We're going to be using the simplest of those equations and only in a cursory way, so that we can practice using our significant figures. I promise you it'll only be as far as plug and chug. And lastly, write very large and very small numbers in scientific notation. Let's start with accuracy and precision. In order to reduce the impact of error, scientists repeat their measurements and calculations many times. If the results are not consistent, they will try to identify and eliminate the source of error. Notice that selecting the right equipment to make measurements is the first step in reducing errors in a measurement. For example, if we are going to be measuring volume, we have a few different instruments we can use. We have a beaker, a buret, or a graduated cylinder. Those all measure volume. The question is, which do we use? If an experimental procedure calls for measuring 8.6 milliliters of a liquid, note that's a fairly small volume, you would use a buret because a buret is well suited for small volumes. The buret allows you to measure a volume of liquid that is as close to 8.6 milliliters as possible. If the procedure calls for measuring 98 milliliters of liquid, you would use a graduated cylinder, specifically a 100 milliliter graduated cylinder, because that instrument is better suited for the task. So when scientists make and report measurements, one factor they consider is a term called accuracy. The accuracy of a measurement is how close the measurement is to the true or actual value. So to understand accuracy, imagine that you throw 4 dots separately at a dartboard. Now note, this next graphic I'm about to show you is going to talk about both accuracy and precision. So even though precision will be defined on a later slide, I'll talk a little bit about it on this graphic. So here we see 3 different dartboards. Each has received 4 darts. In dartboard A, notice that the darts are all clustered in and around the bullseye. So the fact that the darts are within the bullseye means that it's high accuracy, because the true or accepted or intended value is the bullseye, and they're all right on the bullseye. Also notice that they're grouped together. They're grouped very closely to one another. That is what makes the precision high as well. Moving on to dartboard B. The darts are clustered within a small area, but they are far away from the bullseye. Since they are far away from the bullseye, far away from the accepted or intended or true value, that means the accuracy is low. However, the grouping remains tight. So that tight grouping makes the precision still high. So low accuracy, high precision on B. If we look at dartboard C, the darts are scattered around the target, meaning they're not grouped closely together, and they're all far away from the bullseye. So not only do we have low accuracy because the darts are not close to the bullseye, we also have low precision because they're not grouped closely together. Moving on. So suppose the procedure for a chemical reaction calls for adding 36 milliliters of a solution. The experiment is done twice, so 2 different times we attempt to add 36 milliliters of solution. The first time you add a volume, in reality, in actuality, despite your best efforts, you add 35.8 milliliters. And the second time, you add 37.2 milliliters. the first measurement was more accurate because 35.8 milliliters is closer to the true value of 36 milliliters. Again, that is accuracy. Let's contrast that with precision. Another factor that scientists consider when making measurements is precision. Precision is the exactness of a measurement, the exactness. It also refers to the repeatability, the ability to repeat the measurement and actually yield the same value. In other words, it refers to how closely several measurements of the same quantity are made in the same way. So if two measurements are measuring the same quantity in the exact same way, how closely they agree is a measurement of precision. Again, refer back to the idea of the dartboards. So let's refer back to the dartboards.
Accuracy is the closeness of measurements to the correct or accepted value of the quantity measured. Precision is the closeness of a set of measurements of the same quantity made in the same way. Consider a game of darts. The target or accepted value is the bullseye in the center. The person who threw these darts is both precise and accurate. All the darts are grouped very close to the bullseye. This graph shows the results of an experiment that was repeated 4 times. Each time the mass and volume of the product were measured. We see that these results are both precise and accurate. They are clustered and very close to the expected value. This set of throws shows that the dart thrower is precise but not accurate. The darts are grouped very close together, but they have missed the bullseye. Here are the results of another researcher's experiments. These results are precise. The data points are clustered close together, but not accurate. Each of these darts landed reasonably close to the bullseye, but the throws are not clustered together and are not precise. In this experiment, the results would average to a value close to the expected value, so they could be considered accurate. They are not, however, precise. Here we have a set of throws that are neither clustered together nor very close to the target. This set of throws is not precise and not accurate. These experimental results, likewise, are not precise and not accurate. When looking at experimental data, precision lets us know the experiment was done carefully in a controlled environment. Accuracy suggests that the experiment has accounted for all factors that might affect the system being studied.
Moving on to significant figures. When you make measurements or perform calculations, the way you report a value tells about how you got it. And that might not make sense to you right now, but hopefully it will over time. What you need to know is that scientists report values using something called significant figures. The significant figures of a measurement or a calculation consist of all the digits known with certainty as well as one estimated or uncertain digit. The last digit or significant figure reported after a measurement is uncertain or estimated. The very last one is always uncertain or estimated. So remember that idea. All known digits with certainty plus one uncertain digit. Let's look at a picture to see if we can illustrate this. So here we have a nail being measured with a ruler. Now, the units being used here are centimeters. And so I can see most certainly that this nail is over 6 centimeters long. If I look closely, I see that this ruler not only has centimeter markings, but it also has millimeter markings. And so what I can do is I can see that this nail goes to 6.3 centimeters, but not quite to 6.4 centimeters. It's somewhere in between there. And if I look extremely closely, I see it's about halfway between the 0.3 and the 0.4 marking. I know for sure that it's over 0.3, but not yet 0.4. So I know for sure that the 6.3, those two digits are known. But my estimated digit is estimating how far in between 0.3 and 0.4 the tip of that nail is. So I'm going to estimate 5. So I'll actually report 6.35 centimeters for the length of this nail. Reporting all measurements in an experiment to the correct number of significant figures is necessary to be sure the results are true. Imagine you're measuring temperature with a thermometer calibrated to in 1/10 degree increments. For a reading of 36.5 degrees Celsius, the 3 digits in the value are all significant figures. If we look at it closely, we see that of those 3 significant figures, the first 2 digits are known with certainty, while the last digit is estimated. So if we look at these 2 different thermometers, the one on the left is calibrated to in 1 degree increments, while the one on the right is actually calibrated to 1/10 degree increments. Okay, and we see the difference in how exact these 2 thermometers can be, and both of these thermometers are totally useful in their own way. They serve different types of people. One is simply more exact than the other. It uses more significant figures. So there are 4 rules that go along with defining what is a significant figure and what is not. All right, follow along now. Now, we saw when looking at that picture of the nail and the centimeter that when we are making measurements, we list all of the known digits and then 1 estimated digit. That is true. That is when we're making measurements. However, if you're not making a measurement and you are simply given a number, which will happen in this class, I'll just give you numbers to work with, you have to use these 4 rules for figuring out how many significant figures you have. First rule: non-zero digits are always significant. If I include a number that isn't 0, no matter where it is in the number, it is always significant. Always. Rule number 2. Zeros in between non-zero digits are also always significant. Some people call these sandwiched zeros. So if I have 9, 0, 0, 2, those middle zeros are sandwiched in between 2 non-zero digits. Therefore, those 2 zeros are both significant. Rule number 3. Zeros in front of non-zero digits are not significant. These are also known as zeros to the left of a number, or leading zeros is another term you may hear. Leading zeros are never significant. Rule 4 is a little bit more complicated, so you have to see what the condition is. Trailing zeros. So these are going to be zeros after all of the non-zero digits. Trailing zeros. Trailing zeros are only significant if there is a decimal present in the number. That's the condition. If there is a decimal present in the number. Now, it does not matter where in the number. If there is a decimal present in the number, the trailing zeros will be significant no matter where they are. With relation to the decimal, I mean. Now, the trailing zeros are not significant if there is no decimal in the number. If there is no decimal anywhere to be found in the number, all of the trailing zeros are not significant. Be sure to commit those rules to heart. Now, there are some exceptions here. When you use a calculator to find a result, you must pay special attention to significant figures, because a calculator does not round its product, its answer, to the correct number of significant figures. The way a calculator works, it actually assumes that there are an infinite number of significant figures, and so it displays all the numbers it possibly can. Now, in real life, you don't have an infinite number of significant figures, do you? No, you do not. So you have to take that into account when you are writing down your answers, and we will practice that in class. So to determine the number of significant figures in the answer you generated with your calculator, you must first find the number of significant figures in the values you used to calculate the answer. So you have to look at the numbers you plugged into your calculator to figure out how many significant figures to include in your answer. here are some rules to look at when you're actually carrying out calculations. When you're doing multiplication and division, the rule is the answer cannot have more significant figures than the measurement with the smallest number of significant figures. So the least exact number, okay, the fewest significant figures, you find that number, and your answer needs to have that many significant figures. Rule number 2, talking about addition and subtraction, okay, addition or subtraction. The result that you get from your addition or subtraction function, the result can be no more certain than the least certain number in the calculation. So what you're going to do is you're going to look at the values that you're adding or subtracting. You're going to identify the value that has the fewest decimal places past the decimal. The fewest decimal places. Once you find that, your answer has to have that many decimal places. That many decimal places. And you might ask, if a calculation has both addition and multiplication, or the other version like addition and subtraction and multiplication or division, you simply do that rounding function after each and every operation. For example, order of operations, you do your multiplication or division first, figure out your significant figures after your multiplication or division before you move on to do your addition or subtraction. Now, talk about some exceptions or special circumstances when we're talking about significant figures. Some values have an unlimited or infinite number of significant figures. These exact values have no uncertainty. This is what I mean by exact. One type of exact value is a count value. It is determined by counting, not by measuring. For example, a dozen is defined as 12. So you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. A dozen is exactly 12. You can go 0.0 with an infinite number of zeros, exactly 12. And so when we are using potentially the number a dozen as a conversion factor, 1 dozen is equal to 12 units. That 12, we don't look at it as having two significant figures, because the 1 and the 2, we look at it as having an infinite number of significant figures because it is considered a count value. Another value that can have an unlimited number of significant figures is a conversion factor. So when you're making your conversion factors, do not consider those when you are looking at number of significant figures to include in your result. So when you're doing these calculations, ignore both count values and the conversion factors when you're determining the number of significant figures to report. Here's a sample problem. I'm going to work this out for you. We're going to start working with energy. So just, keep your caps on and do not be intimidated. Follow along and try to stay with me. A student heats 23.62 grams of a solid and observe that its temperature increases from 21.6 degrees Celsius to 36.79 degrees Celsius. Calculate the the temperature increase per gram of solid. All right. So what are we being asked to do? Calculate the temperature increase. That's not it. Not just the temperature increase. That would simply be the difference between the two temperatures, initial and final temperature. But it's per gram. Per gram. So we have to take into account how many grams of the solid there is. So how would we work this out? We're first going to find the temperature change by subtracting the initial temperature from the final temperature. All right, that'll give us the temperature increase. And plugging in those numbers, we find that the temperature increase is 15.2 degrees Celsius. Now notice 36.79 degrees Celsius has 4 significant figures and 21.6 degrees Celsius has 3 significant figures. We're doing addition and subtraction. So how many significant figures should I use? I look at the least exact number. I see that 21.6 degrees Celsius only has 1 decimal place past the decimal. So my answer needs to have 1 decimal place past the decimal. So that's why, even though the calculator will tell us that 15.19 is our answer, we need to round to that first decimal place. So we actually want to report 15.2 degrees Celsius as our temperature increase. Now we're being asked to measure the temperature increase per gram of solid. We simply just calculated the temperature increase. So we calculate the temperature increase per gram of solid by dividing the temperature increase, what we just determined, by the mass of the solid. So we'll take the temperature increase, divide it by how many grams, plug in those numbers, and we get an answer of 0.644 degrees Celsius per gram. And notice that we're including 3 significant figures because 15.2 degrees Celsius has 3 significant figures, and we are using division. In the reading, you'll see that the specific heat is the quantity of energy that must be transferred as heat to raise the temperature of 1 gram of a substance by 1 Kelvin. Specific heat depends on the nature of the material that is changing temperature, the mass of the material, and the size of the temperature change. For example, iron has a larger specific heat than silver. Therefore, more energy as heat can be transferred from iron than to silver. Specific heats can be used to compare how different materials absorb energy as heat under the same conditions. The specific heat, which is represented by C sub P of a substance at a given pressure, represented as P, is calculated by the following formula. You're going to need to copy this down. Note that Q is the energy transferred as heat. M is the mass of the substance, and delta T is the difference between the initial and final temperatures. So we now have the definitions for all of the terms present here. Let's work on a sample problem. Be sure to refer to this equation as we work through the sample problem. A 4.0 gram sample of glass was heated from 274 Kelvin to 314 Kelvin and was found to absorb 32 joules of energy as heat. Calculate the specific heat of the glass. First, I want to determine the delta T, the change in temperature, by calculating the difference between the initial and final temperatures. Insert the other values into the equation for calculating specific heat and calculate. That my specific heat is equal to the 32 joules, right? That's Q, 4.0 grams, that's M, the mass, multiplied by delta T, the change in temperature. Doing some calculations, I see that delta T is actually 40 Kelvin. And so I simply plug into my calculator 32 divided by 4 times 40. And you will get 0.20. And the units here, if you are following the units, you have joules divided by grams times Kelvin. Moving on to scientific notation. Very large and very small numbers are often written in scientific notation. A number in scientific notation has 2 parts. The first part is a number that is between 1 and 10. The second part is a power of 10. To write the first part of the number, move the decimal, for whatever value you're working with, move the decimal to the right or to the left so that the only non-zero digit, that there is only one non-zero digit to the left of the decimal. Write the second part of the value as an exponent. This part is determined by counting the number of decimal places the decimal point is moved. If the decimal point is moved to the right, the exponent is negative. If the decimal is moved to the left, the exponent is positive.
Scientists sometimes need to express measurements using numbers that are very large or very small. For example, the speed of light through space is about 3 billion meters per second. 9 zeros is a lot of zeros to keep track of when performing a calculation. You can express values as a number multiplied by a power of 10. This is called scientific notation. There are 9 decimal places to the right of the 3 in 3 billion. So using scientific notation, the speed of light through space is written as 3 times 10 to the 9th meters per second.
When we're using scientific notation in calculation, we have a few rules to follow. In scientific notation, exponents are count values, so you do not look at significant figures when considering the exponents, or when you look at the exponents, you don't consider significant figures. In addition to addition and subtraction problems, all values must have the same exponent before they are added or subtracted. I'll repeat that. When doing addition and subtraction problems, all values must have the same exponent before they can be added or subtracted. So, if you have differing exponents, you're going to have to move the decimal of one of the values until you have the same exponent. Then you can carry out your function. The result is the sum of the difference of the first factors multiplied by the same exponent of 10. In multiplication problems, the first factors of the numbers are multiplied and the exponents of 10 are added. When you're multiplying, the exponents are added. However, in division problems, the first factors of the numbers are divided, but the exponents of 10 in the denominator is subtracted from the exponent of 10 in the numerator. You actually are calculating the difference between the exponents of 10. So, scientific notation when considering significant figures. Use scientific notation to eliminate all place-holding zeros. That's another way of saying all of the zeros that end up being not significant. And lastly, move the decimal in the answer so that only one digit is to the left, and change the exponent accordingly. The final value must contain the correct number of significant figures, and if it doesn't, you round until it does. Alright, that's the end of this video lecture. I will see you next period.